The universe is mostly empty space, but this emptiness isn't just a backdrop. It plays a critical role in shaping everything we see. Vast regions called voids stretch across the cosmos, containing almost no matter, yet they influence the formation of galaxies, the movement of energy, and even the way the universe expands. These sparse regions are home to unique phenomena like cold hydrogen clouds and faint waves of energy that reveal clues about the early universe and its evolution. Studying these empty spaces helps us understand the hidden forces that shape the cosmos and the fundamental nature of the universe itself. Join me as we try to uncover the secrets of this emptiness. The Eridanus supervoid, a puzzle of cosmic scale. The Eridanus supervoid stretches across more than 1 billion light-years, a staggering expanse of near-total emptiness. This supervoid is a region where the density of matter is significantly lower than the already sparse intergalactic space. Over 1 billion light-years of sheer volume lacks not only stars, but also the faint traces of gas and dust that permeate most regions of the universe. The size and scope of the Eridanus supervoid suggest an origin tied to quantum fluctuations during the inflationary period of the early universe. Inflation, a brief moment of exponential expansion shortly after the Big Bang, left imprints on the distribution of matter and energy. Tiny quantum fluctuations in this era could have been stretched to cosmic scales, creating regions of high and low density. The Eridanus supervoid might represent one of these low-density areas, where matter failed to coalesce into galaxies and clusters. Studying the void's properties provides a unique opportunity to probe the conditions of the universe in its infancy. The cold spot associated with the Eridanus supervoid has fueled speculation about interactions with the multiverse, a theoretical framework suggesting the existence of multiple, potentially infinite, universes. Some researchers propose that the supervoid could be a region where our universe interacted with another universe during or after inflation. This interaction might have altered the distribution of matter, creating the vast emptiness observed today. While speculative, this hypothesis underscores the supervoid's significance as a potential bridge between observational cosmology and theoretical physics. It also highlights the need for further research to test these ideas against empirical data. One thing that makes the Eridanus supervoid unique is that there have been no galaxy groups for more than 1 billion years. The thick threads of the cosmic web are usually made up of galactic clusters, which are groups of hundreds or thousands of galaxies that are held together by gravity. The fact that there are no such groups in the supervoid makes its very low density stand out. This lack of something changes not only the local gravity field, but also how light, matter, and energy move in and around the void. Because galaxies aren't common in this area, it's a great place to study the edges of big cosmic structures and the processes that make them grow. Light traveling through the Eridanus supervoid experiences significant weakening due to the vast expanse of emptiness. Photons lose energy as they traverse the void, a process that amplifies redshift and dims light signals from distant sources. This effect complicates efforts to observe galaxies and other cosmic objects beyond the void, as their light is stretched and diminished. The weakening of light also impacts our ability to map the void's internal structure, as traditional methods of detecting baryonic matter rely on the interaction of light with particles. These challenges necessitate the use of advanced observational techniques, such as gravitational lensing, to probe the void indirectly. Quantum vacuums, the emptiest state possible. Quantum vacuums are often described as the emptiest state imaginable, yet their emptiness is deceptive. These regions, devoid of ordinary matter, teem with dynamic processes governed by quantum mechanics. Unlike the emptiness of cosmic voids, quantum vacuums operate on a subatomic scale, revealing a bustling world of virtual particles, fluctuating energy fields, and space-time distortions. At the heart of quantum vacuums are virtual particle fluctuations. These transient particles momentarily appear and vanish due to the Heisenberg uncertainty principle, which allows energy to exist in brief, fleeting intervals. Virtual particles are not directly observable, but their effects are measurable. For instance, they contribute to the Casimir effect and even play a role in the forces binding atoms. In quantum vacuums, these fluctuations are ever present, creating a dynamic environment where the distinction between something and nothing becomes blurred. This ceaseless activity supports the propagation of energy fields through nothing. In classical physics, a vacuum might be imagined as a void, devoid of any matter or interaction. Quantum mechanics, however, shows that even in the absence of matter, energy fields persist. The electromagnetic field, for example, allows virtual photons to arise and influence charged particles. The Higgs field, another pervasive energy field, imparts mass to fundamental particles. These interactions demonstrate that the emptiness of a quantum vacuum is a fertile ground for fundamental processes that define the universe. The idea of quantum foam, which was put forward by scientist John Wheeler, is one of the more vague but interesting parts of quantum vacuums. Quantum foam describes a swirling, disorganized structure at the very small sizes of spacetime. Quantum uncertainty means that space and time are not smooth or continuous. Instead, they change over time. These changes show up as tiny bubbles of spacetime that are always shifting and warping because of energy fields. Quantum foam can't be seen directly, but many ideas in quantum gravity and string theory are based on its effects. This suggests that it may be the key to understanding how fundamental forces can be brought together. It is very important to tell the difference between quantum vacuums and cosmic voids. There are huge areas called cosmic gaps where the quantity of matter is very low, like a few atoms per cubic meter. This empty space is formed by the big structure of the world and the way gravity acts on it. In comparison, quantum vacuums are on the Planck scale, which means that regular matter can't exist in them. There is some baryonic matter in cosmic gaps, but none at all in quantum vacuums. They are made up of energy fields and virtual particles, and are therefore pure quantum settings. The comparison shows how emptiness shows up in very different ways at very different sizes. This absence of baryonic matter, the ordinary matter composed of protons, neutrons, and electrons, creates a unique stage for quantum processes. Without interference from traditional particles, quantum vacuums allow the underlying quantum fields to dominate. These fields interact in complex ways, creating forces and particles that influence the macroscopic world. The vacuum's absence of matter also provides a pristine environment for testing fundamental theories, such as quantum electrodynamics, QED, and quantum chromodynamics, QCD, which govern particle interactions and forces. Gravitational waves, ripples in spacetime caused by massive objects in motion, interact with quantum vacuums in ways that are only beginning to be understood. As these waves propagate, they influence the quantum fields within the vacuum, creating subtle shifts and fluctuations. These interactions are two-way. The quantum vacuum might also modify the behavior of gravitational waves, altering their speed or amplitude. While these effects are subtle, they provide an opportunity to connect quantum mechanics with general relativity, bridging the gap between the very small and the very large. Advanced detectors, such as those used for gravitational wave astronomy, may one day observe these phenomena directly. The Casimir effect is an experiment that shows that there is action in quantum vacuums. There is a small force pulling two metal plates together when they are close together in a vacuum. There is a force because the plates limit the ranges of virtual particles that can be between them. This makes a pressure difference. Hendrik Casimir was the first person to predict the effect in 1948. Since then, it has been measured with greater accuracy, showing clear proof of vacuum changes. This event isn't just an interesting academic curiosity, it has real-world effects on nanotechnology and the design of MEMS. Microelectromechanical systems. Changes in virtual particles are also a key part of the puzzle that shows why the vacuum is never really empty. Even when there are no particles that can be measured, quantum fields are still changing. The energy level inside the vacuum is caused by these changes. This energy is called vacuum energy. It is thought that this energy abundance has something to do with the expansion of the universe. It could be a link between quantum vacuums and dark energy, the unknown force that is speeding up the expansion of the universe. Energy fields moving through quantum vacuums are another example of how things that seem to be different are actually linked. For example, electromagnetic fields make it easier for charged particles to trade virtual photons with each other. This is what makes electromagnetic forces possible. In the same way, the Higgs field works in the void, giving particles mass through the Higgs process. These fields show that the world is full of activity that changes the basic rules of nature, even when there is no matter what. The roiling activity of quantum foam represents spacetime at its most fundamental level. The foam-like structure suggests that space and time themselves are not static, but dynamic, continuously fluctuating in response to energy and quantum uncertainty. These fluctuations could create minute wormholes or other distortions in spacetime, which, though fleeting, hint at possibilities for exotic phenomena like quantum tunneling on a cosmic scale. Quantum foam might also provide clues to understanding the Big Bang and the unification of gravity with quantum mechanics. Although quantum vacuums and cosmic voids both stand for nothingness, their physical properties are radically different. The dispersion of dark matter and the force of gravity combine to form cosmic voids, which are large areas devoid of galaxies. However, in quantum field theory, fields and particles are characterized as being in states of perpetual fluctuation, which is why quantum vacuums exist. Dark energy's playground. Regions with no resistance. Dark energy is the unknown force that is speeding up the growth of the universe. It is best studied in places with little interference, and cosmic voids are just that, because there is almost no baryonic matter or gravity pull in these huge empty areas. They are the perfect place to test ideas about dark energy. In contrast to dense areas packed full of galaxies, voids let dark energy take over, since the gravity pull of large objects doesn't hide it. Voids, especially supervoids spanning millions of light years, are considered ideal grounds for testing dark energy theories. The absence of significant mass means that gravitational forces are minimal, allowing scientists to observe the pure effects of dark energy. In such regions, the universe's expansion accelerates at a rate that is directly influenced by dark energy's properties. Observing the motion of matter around these voids, or the lack thereof, provides clues about the fundamental nature of this enigmatic force. By focusing on voids, researchers can isolate the effects of dark energy, stripping away the complexities of gravitational interactions that dominate elsewhere. Supervoid centers exhibit near-null gravitational pull, making them fascinating focal points for studying dark energy. Unlike galaxy clusters or dense filaments of the cosmic web, where gravity competes with expansion, these centers allow dark energy to take the lead. Matter in these regions is so sparse that there is little to counteract the repulsive effect of dark energy, creating a near-perfect vacuum. Observing the dynamics of supervoids provides a glimpse into how dark energy shapes the universe on the largest scales. Measurements of redshift, galaxy velocities, and large-scale flows within these regions shed light on the interplay between dark energy and gravity. The lack of gravitational resistance in supervoids leads to expansion rates that are significantly enhanced compared to denser areas. Dark energy, often described as a cosmological constant or as quintessence, acts more freely in these vast empty spaces. As a result, the local expansion of space accelerates, stretching voids even further. This amplified expansion makes supervoids an excellent testing ground for the equation of state of dark energy, which defines how its energy density changes over time. Observing these expansion rates offers critical data to distinguish between competing models of dark energy, including those that propose dynamic, evolving forms of the force. Quintessence fields, theoretical energy fields that could drive dark energy, find a natural home in these desolate regions. Unlike the cosmological constant, which posits a uniform energy density across space, quintessence allows for spatial variations in dark energy's effects. In voids, where gravitational and baryonic interference are minimal, these variations might be more apparent. Mapping quintessence fields in these regions could provide insight into their structure and behavior, revealing whether dark energy is truly uniform or influenced by local conditions. This understanding could redefine our understanding of cosmic acceleration and the ultimate fate of the universe. Desolate regions such as voids mirror inflationary principles, providing a connection between the universe's earliest moments and its current accelerated expansion. During inflation, the universe experienced a brief but dramatic period of exponential growth, driven by a field similar to dark energy. Voids, with their amplified expansion rates and minimal gravitational pull, offer a microcosm of these early conditions. Studying these regions could reveal parallels between inflation and dark energy, suggesting that the same fundamental forces might be at play. Observations in voids could also help refine models of inflation, linking the universe's birth with its ongoing evolution. Unknown one-dimensional flaws in space-time called cosmic strings might also find a special place to be tested in gaps. Some models of the early universe suggest that these things will exist. They could be the cause of gravitational waves or other strange events. In areas with a lot of thick objects, the weak signs that cosmic strings might send are hidden. But in voids, where there is no major mass, these signs can be seen more clearly. Researchers could find proof that cosmic strings exist and play a part in creating the universe by looking for gravity waves or strange changes in the cosmic microwave background inside empty spaces. The interplay of dark energy, gravitational forces, and cosmic structure formation is uniquely observable in the emptiness of voids. These regions amplify the effects of dark energy, allowing its influence on the universe's expansion to be studied in detail. Whether through the accelerated stretching of space, the behavior of quintessence fields, or the echoes of inflation, voids provide a natural arena for probing the mysteries of dark energy. Supervoid centers, with their near-null gravitational pull, further isolate these phenomena, offering a clearer view of how dark energy operates in the absence of matter. By looking into gaps, scientists can improve cosmological models and learn more about how dark energy affects the placement of galaxies and how cosmic structures change over time. It helps to connect what we know about how the world works on a big scale to the basic forces that control it. Researchers can look into the effects of dark energy and other possible things, like cosmic strings, because there is no pushback in these areas. Absence of magnetic fields in intergalactic space. In galaxies and clusters, magnetic fields are built into the dense matter, but in cosmic voids, the conditions aren't right for organized magnetic flows to happen. In order to form and keep their shape, magnetic fields need charged particles and moving currents, but these things are almost never found in intergalactic space because it is so empty. Without coordinated flows, the magnetic fields in these areas stay small, broken up, or can't be found at all. In regions where magnetic fields are present, they often arise from seed fields that are later amplified by processes such as turbulence or gravitational collapse. These seed fields are typically minuscule, created during the early stages of the universe, or through phenomena like stellar winds and supernovae. However, in intergalactic space, the seed fields are too weak to undergo amplification. Without the density and energy provided by plasma flows or violent astrophysical events, these fields remain static, barely detectable against the cosmic backdrop. Their weak nature highlights the unique and quiet conditions of the intergalactic voids. The lack of coherent magnetic flows is closely correlated with the low plasma densities found in intergalactic space. Plasma, a state of matter consisting of charged particles, is a key medium for sustaining magnetic fields. In galaxies and clusters, plasma density is high enough to support magnetic turbulence and dynamo mechanisms, which amplify seed fields into coherent structures. However, in the near-perfect vacuum of intergalactic voids, plasma densities are so low, often just a few particles per cubic meter, that these processes cannot take place. The sparse plasma fails to generate the currents needed to sustain magnetic fields, resulting in an environment where magnetism is almost non-existent. Despite this absence, intergalactic space may still hold traces of primordial magnetic fields that originated in the early universe. These fields, imprinted during or shortly after the Big Bang, could have been distributed throughout the cosmos. Tracking these lost traces of primordial magnetism is a challenge, but they may hold vital clues about the universe's earliest moments. If detected, these fields could reveal the processes that shaped the large-scale structure of the universe and provide insights into the conditions of the cosmos shortly after its formation. Faraday rotation studies have become a crucial tool for investigating the presence of magnetic fields in intergalactic space. Faraday rotation occurs when polarized light passes through a magnetized medium, causing the plane of polarization to rotate. By observing the light from distant quasars and galaxies as it travels through intergalactic voids, researchers can measure any subtle Faraday rotation effects. These measurements help map the presence and strength of magnetic fields along the line of sight. So far, the lack of significant Faraday rotation in many intergalactic regions supports the conclusion that coherent magnetic fields are largely absent in these spaces. Detecting ancient cosmic magnetism in intergalactic space remains one of the great challenges of modern astrophysics. Advanced techniques and instruments, such as radio telescopes capable of measuring faint polarization signals, are being developed to search for these elusive fields. If remnants of primordial magnetic fields are found, they could provide a direct link to the processes that shaped the universe's infancy. Such discoveries would not only fill gaps in our understanding of cosmic magnetism, but also offer a window into the physics of the early universe, including the nature of dark matter and energy. The implications of weak or absent magnetic fields in intergalactic space extend beyond the immediate question of magnetism itself. Magnetic fields play a significant role in shaping cosmic evolution by influencing the behavior of charged particles, plasma flows, and even the formation of large-scale structures. The lack of strong magnetic fields in intergalactic voids means that these regions evolve under different conditions compared to galaxies or clusters. Understanding how these voids remain largely unaffected by magnetism helps refine models of cosmic evolution and the interplay between gravitational and electromagnetic forces. Since there are no unified magnetic fields in cosmic space, it is a great place to know how other forces, like gravity and dark energy, interact with each other without having to deal with magnetism. This lack also makes us wonder where magnetic fields came from and how they are spread out in the world. Were the magnetic fields in the beginning of time smaller or less widespread than we thought? Or were the factors needed to boost these areas just not present in some places? Lyman alpha forests. The Lyman alpha forest is a complicated and interesting part of the world that shows how big and complicated it all is. They are just patterns of absorption lines seen in the light from galaxies and quasars far away. Each line shows the amount of neutral hydrogen in the universe, which is the most common element. Light from a quasar or galaxy moves through the space between galaxies and comes across areas of neutral hydrogen. The Lyman alpha absorption lines are made when these atoms take in light at a certain frequency. These sparse absorption lines reveal the locations of neutral hydrogen pockets scattered across the universe. The patterns they form are not uniform. Instead, they map the distribution of hydrogen across intergalactic space. Each line corresponds to a specific redshift, reflecting the distance and velocity of the hydrogen clouds relative to Earth. By analyzing these absorption lines, astronomers can create a three-dimensional map of the large-scale structure of the universe. The Lyman alpha forest becomes a tool for tracing the cosmic web, revealing the connections between galaxies, clusters, and the vast voids that lie between them. When Lyman alpha signs aren't present in certain areas as when they are. Gaps in the Lyman alpha forest show places where there is little or no neutral hydrogen. These holes are often lined up with cosmic deserts, which are places with very little matter density and few galaxies and gases. Astronomers can find and describe the biggest holes in the universe by making maps of these gaps. The lack of thick gas structures in these areas is very different from the crowded conditions in galaxy clusters and filaments, showing how different conditions are at different sizes in the universe. Ionizing radiation plays a critical role in shaping the patterns of the Lyman alpha forest. This radiation, emitted by quasars, young stars, and other energetic sources, strips electrons from hydrogen atoms, transforming neutral hydrogen into ionized plasma. During the epoch of reionization, which occurred several hundred million years after the Big Bang, the first stars and galaxies emitted intense ionizing radiation, reionizing the universe and creating vast regions free of neutral hydrogen. The Lyman alpha forest captures this transformation, with absorption lines marking the boundaries between ionized and neutral regions. The interplay between ionizing radiation and hydrogen distribution continues to shape the forest, offering insights into the energetic processes that govern the universe. The connection between Lyman alpha forests and reionization epochs is profound. The forest reflects the state of the intergalactic medium during different periods of cosmic history. During reionization, the first sources of light began to ionize their surroundings, creating bubbles of ionized hydrogen that expanded over time. These bubbles eventually overlapped, reionizing the entire universe. The Lyman alpha forest contains the imprints of this era, preserving the history of how light and matter interacted in the early universe. By studying the forest, astronomers can reconstruct the timeline of reionization, determining when and how the first galaxies transformed their surroundings. The density of the Lyman alpha forest varies near intergalactic deserts, reflecting the local distribution of hydrogen and galaxies. In dense regions, the forest appears crowded, with many absorption lines indicating numerous pockets of neutral hydrogen. Near voids and deserts, however, the forest becomes sparser, with fewer lines marking the absence of significant hydrogen. These differences in density provide a means of mapping the transition between dense cosmic structures and the emptiness of voids. The forest serves as a bridge, connecting the rich environments of galaxies to the desolate expanses of intergalactic space. Lyman alpha gaps are very useful for showing how few galaxies there are. These areas don't have any Lyman alpha absorption lines, so they are made up of places where there are few or no galaxies. Because there aren't any galaxies, stars aren't forming very often, and there aren't many other processes that make radiation that hydrogen clouds stay neutral. Because of this, these gaps are some of the universe's emptiest and purest places. Cosmic expansion and the stretching of emptiness. The redshifts of faraway galaxies were the first signs of cosmic expansion, which is the ongoing stretching of space itself. One of the most interesting things about this growth is that it happens at different speeds in different parts of the world. In places with a lot of mass, like galaxy groups, the growth is slowed down by the pull of mass. Voids, on the other hand, which are large areas of space that are almost entirely empty of matter, expand more quickly. Dark energy's effects are stronger in empty spaces because there aren't any strong gravity pulls there. This makes space stretch faster. A big part of the faster stretching process is that there is no mass in open areas. However, in galaxy groups and filaments, gravitational pull holds galaxies and matter together, even though the universe is expanding as a whole. Voids, on the other hand, don't have enough mass to make this reaction. Because dark energy doesn't depend on gravity, its impacts can happen without any problems. Because of this, gaps have a faster rate of growth than denser areas, so they grow faster and stretch farther. This phenomenon aligns with Einstein's theory of general relativity, but introduces a paradox often referred to as the problem of moving nothing. In cosmic voids, there is so little matter that space itself seems to expand without anything tangible to stretch. The paradox lies in how relativity explains the behavior of space-time in such emptiness. According to the theory, mass and energy shape space-time, yet in regions with almost no mass, space still expands. Redshift measurements provide crucial data for understanding how voids expand differently from denser regions. As light from distant galaxies travels through cosmic voids, the expansion of space stretches its wavelength, causing it to shift toward the red end of the spectrum. By studying the redshifts of galaxies located in and around voids, astronomers can determine how quickly these regions are growing. These measurements not only confirm that voids expand faster than clusters, but also offer insights into the properties of dark energy, such as its equation of state and its impact on the universe's expansion history. Cosmic voids are also used to study cosmic acceleration as calibration points. Because they are simple and don't have the complicated gravitational effects of filaments and groups, they are perfect for tracking the effects of dark energy. Scientists can improve models of cosmic acceleration and learn more about how the universe works on a large scale by comparing the growth rates of holes and denser regions. Voids give us a clear picture of how space expands when there is no mass in it. They act as a cosmic standard. Gravitational waves are ripples in space-time that are caused by very large cosmic events. They deal with empty spaces differently than they do with packed areas. Matter in clusters and galaxies causes barriers that can slow down or bend gravitational waves as they move through them. In gaps, on the other hand, this resistance is very low or non-existent, which lets the waves move more easily. Since there isn't much mass in these areas, the blurring effect is lessened, making the signal easier to see. Finding out more about gravitational waves in empty space could help improve models of how space-time works and give us new information about how cosmic expansion and gravitational effects interact. Cosmic microwave background. The cosmic microwave background, CMB, is often referred to as the afterglow of the Big Bang, a faint radiation that fills the universe and carries with it a snapshot of the cosmos in its infancy. This radiation, detected as a nearly uniform glow, has subtle temperature variations that reveal the distribution of matter and energy shortly after the universe's birth. Among these variations are cold spots, regions where the CMB's temperature is slightly lower than average. These cold spots represent areas of extreme emptiness, often associated with underdense regions in the large-scale structure of the universe. These cold spots arise from primordial fluctuations in the early universe's density. During the epoch of recombination, around 380,000 years after the Big Bang, photons were released as the universe cooled and neutral hydrogen formed. At this time, slight variations in density existed across the universe. In regions of higher density, matter clumped together, forming the seeds of galaxies and clusters. However, in underdense regions, matter was sparse, preventing the formation of significant structures. These primordial fluctuations left imprints on the CMB, with underdense regions appearing as cold spots due to their weaker gravitational pull and lack of significant matter to retain heat. Some strange things in the CMB, like spots that are very big or very cold, make the normal model of the universe look like it's not quite right. Based on isotropic ideas, the world should look the same from all sides at the biggest scales. But these strange things, like the well-known CMB cold spot found in the southern hemisphere, don't follow these rules. Some scientists think that these strange events might just be statistical accidents, but others think of more unusual reasons, like the possibility of cosmic textures, which are flaws in space-time left over from phase changes in the early universe. These strange things make us wonder if what we know about the early physics of the universe is full, or if we need to learn more about it in order to explain these things. There is a strong link between these cold spots and the structure of the universe on a big scale, because cosmic gaps and temperature drops in the CMB are linked. Void regions are places hundreds of millions of light-years across that are not dense with galaxies, gas, or matter. The changing gravity potential inside the gaps changes the energy of the CMB photons as they move through them. The integrated Sachs-Wolf ISW effect indicates that photons lose energy as the universe grows. This leads to cooler temperatures in the CMB. Scientists have made the link between the CMB's temperature changes and the structure of the cosmic web stronger by looking at how voids and temperature drops are aligned. The untouched nature of these void regions offers a unique window into the early universe. Many voids remain relatively unchanged since the universe's infancy, serving as a time capsule preserving the primordial conditions shortly after the Big Bang. These voids are thought to have formed from initial underdense fluctuations, which were unable to draw in enough matter to form stars, galaxies, or other structures. Their immense scale, some spanning over 1 billion light-years, makes them critical areas for understanding how the universe evolved. Unlike denser regions that have undergone significant change due to gravitational interactions, voids provide a pristine view of the conditions that existed at the time of recombination. The suppression of higher harmonics in low-density regions is another intriguing feature of the CMB. The temperature fluctuations of the CMB can be analyzed through their power spectrum, which is divided into spherical harmonics representing different angular scales. Higher harmonics correspond to smaller scale fluctuations, which are shaped by the interaction of matter and radiation in dense regions. In voids, where the density of matter is significantly lower, the gravitational potential wells are shallow. This leads to the suppression of smaller scale fluctuations, resulting in smoother temperature variations over larger scales. This lack of higher harmonics in void regions aligns with observations and offers further confirmation of the role of gravitational potential in shaping the CMB. The standard model of cosmology predicts a certain pattern of temperature fluctuations in the CMB based on the distribution of matter and energy in the early universe. However, deviations such as the lack of higher harmonics in voids or the presence of large anomalies challenge these predictions, suggesting there may be gaps in our understanding. These anomalies could point to new physics, such as interactions between dark energy and matter, or hint at processes that occurred during or shortly after the inflationary epoch. The strange things in the CMB, especially the cold spots, make us think about how outside forces, like relations with the multiverse, might be affecting the CMB. Some scientists think that big cold spots could be caused by our universe and other bubble universes colliding during the inflationary time. These exchanges might leave marks in the CMB that look like they are not following the usual isotropic pattern. Even though this is just a guess, it shows that the CMB might be able to show things that aren't explained by normal cosmology. Scientists are learning more about these questions with the help of new tools and methods for observation, like the Planck satellite and the soon-to-be-launched CMBS-4 studies. Researchers can better look at cold spots, void correlations, and the reduction of higher harmonics if they map the CMB with higher precision and sensitivity. Relic neutrinos in empty regions. Some of the most interesting leftovers from the Big Bang are relic neutrinos, which are particles that have been around for billions of years and show how the universe began. These particles are part of the cosmic neutrino background, CVB, which is an old type of radiation like the cosmic microwave background, CMB, but made up of neutrinos instead of photons. Relic neutrinos were created about 1 second after the Big Bang. As the universe has grown, they have cooled and slowed down, becoming some of the oldest and most mysterious parts of the universe. Their features and actions, especially in the incredibly empty spaces called cosmic gaps, are very important for understanding how the universe started and how it is still changing. Relic neutrino zones are the best places to study these particles because they almost never have baryonic particles. Baryonic matter which is made up of protons, neutrons, and electrons, has clumped together into galaxies, stars, and other dense structures, leaving huge gaps that are almost devoid of it. But relic neutrinos don't behave in this way when they cluster. Because they don't interact strongly with other particles and were separated from the hot plasma of the early universe early on, they stay spread out evenly, even in the most empty parts of the universe. Because they are not affected by gravitational clustering, relic neutrinos give scientists a unique chance to study their features in places where other types of matter don't interact with them much. Within supervoids, the density of relic neutrinos may exhibit subtle variations compared to denser regions. While relic neutrinos are expected to be evenly distributed due to their early decoupling, the gravitational potential of large-scale cosmic structures can create slight perturbations. Supervoids, with their lower gravitational influence, might have marginally lower neutrino densities than clusters or filaments. These differences, while incredibly small, are valuable for understanding how neutrinos interact with the large-scale structure of the universe. Measuring these variations requires highly sensitive observational techniques, as they could provide insights into the interplay between neutrinos, dark matter, and the expanding universe. Finding leftover neutrinos is still one of the hardest things in modern physics. Since they were first made, these particles have cooled down a lot. Their energies are now on the order of microelectron volts, which is well below what most detectors can measure. Unlike neutrinos with higher energies that are made by supernovae or cosmic rays, relic neutrinos have very weak interactions with matter. This means that they are very hard to directly detect with the technology we have now. Though new methods, like using very sensitive cryogenic monitors or looking at how their gravity affects big buildings, give us hope for future breakthroughs. Finding relic neutrinos would give scientists a new way to look into the early universe and study what it was like just seconds after the Big Bang. It is harder to find void neutrino regions because they don't have any thermal traces. As electromagnetic radiation, like heat or light, is given off by baryonic matter, it is easy to view with binoculars and other tools. Relic neutrinos, on the other hand, don't give off heat, so they can't be seen using normal observing means. They can't be seen directly, so we have to figure out that they are there by looking at things like how their weak gravity pull affects other particles or how they interact with cosmic background radiation. Even though they happen very rarely, these interactions could provide important proof of the presence and features of relic neutrinos. Cosmic expansion has profoundly shaped the behavior of relic neutrinos, dispersing them uniformly across the universe while reducing their energy. In the moments following the Big Bang, these particles were highly energetic, moving at relativistic speeds. As the universe expanded and cooled, the energy of relic neutrinos decreased, causing them to slow down and transition to a more diffuse, non-relativistic background. This process, known as redshifting, is analogous to how light from distant galaxies stretches into longer wavelengths as space expands. The energy loss from cosmic expansion has made relic neutrinos more challenging to detect, but has also spread them across even the emptiest regions of space, embedding them within cosmic voids. Relic neutrinos patterns hold important information about how the Big Bang worked. When these particles broke away from the hot plasma of the early universe, it was less than a second old. They took a picture of the universe at that point in time with them. Their even spread and low energy today show how hot, dense, and quickly expanding the universe was when it was first formed. Scientists can improve their models of cosmic inflation, the fast growth that happened a few hundredths of a second after the Big Bang, by looking at these trends. The way relic neutrinos behave gives us a unique look into the physical processes that made the universe when it was first being formed. While neutrinos themselves are not dark matter, their weak interactions and near invisibility make them a useful analog for studying dark matter particles. Both relic neutrinos and dark matter share the characteristic of being nearly undetectable through electromagnetic radiation, requiring indirect methods to study. Observations of neutrino behavior in cosmic voids could offer parallels for understanding dark matter's distribution and influence on the universe's structure. Relic neutrinos are also very important for figuring out how the world is put together on a large scale. When they first broke apart, they were able to move around the universe easily, not being affected by the gravity clustering that made galaxies and clusters out of baryonic matter. So, leftover neutrinos give us a unique starting point for understanding how matter and energy are spread out on a cosmic scale. The way they behave in empty spaces, where gravity doesn't have much of an effect, provides a clean testing ground for studying the basic forces and interactions that control the world. Relic neutrinos might be the key to finding answers to some of the most important questions in particle physics. You need to know about their qualities, like how their mass and flavors change, in order to understand the standard model of particle physics and its flaws. Neutrinos' mass finding, for example, has already called into question the original version of the standard model, which has led to the discovery of new physics. Some ideas for finding them are to look at the mark that relic neutrinos left on the big picture structure of the universe, or to use very sensitive devices that can pick up the rare interactions between neutrinos and other particles. Isolated pulsars in cosmic wilderness. Pulsars are neutron stars that spin very quickly and were made when huge stars exploded. As these thick city-sized pieces spin, they send out beams of electromagnetic energy from their magnetic poles, making a signal that looks like a lighthouse. A lot of pulsars stay in the thick surroundings where they were born, but some are thrown out into space and travel long distances by themselves. These wanderers, lost in the empty space between galaxies, provide a rare and special chance to study how very large pieces of stars interact with the vastness of the universe. The journey of isolated pulsars often begins with the powerful kick they receive during their formation in a supernova explosion. When a massive star exhausts its nuclear fuel, it collapses under gravity, leading to a violent ejection of its outer layers. This asymmetric explosion generates a recoil effect that propels the newly formed neutron star at incredible speeds, sometimes exceeding 1,000 kilometers per second. These supernova kicks can eject pulsars from their host star clusters, or even their parent galaxies, sending them on solitary trajectories through the cosmic void. Over millions or billions of years, these pulsars traverse immense distances, becoming solitary wanderers in the intergalactic wilderness. In the wide vacuum, the low-density environment affords optimal circumstances for researching pulsar intrinsic features. One such attribute is the spin-down rate, which indicates how rapidly a pulsar's spinning decreases over time. Pulsars lose rotational energy largely through the emission of electromagnetic radiation and particle winds, which gradually reduce the spin rate. In dense settings, interactions with surrounding material, magnetic fields, and neighboring stars can speed up the process. However, in the near vacuum of cosmic gaps, these external forces are reduced. This isolation enables scientists to investigate the pure forces causing spin-down, yielding information on the pulsar's magnetic field strength, internal structure, and energy loss processes. Isolated pulsars are defined by their lack of detectable companions or surrounding stars. In galactic environments, pulsars often exist in binary systems or clusters, where gravitational interactions with other stars affect their motion, spin, and emission characteristics. Isolated pulsars, by contrast, have been cast adrift, severed from such gravitational relationships. This solitude simplifies their observational profiles, enabling researchers to focus solely on the pulsar without accounting for the influence of nearby objects. Moreover, their isolation underscores the immense distances they have traveled, highlighting the dramatic events that expelled them from their original stellar nurseries. The unique electromagnetic environment of cosmic voids influences the emissions of isolated pulsars, resulting in variances compared to pulsars in denser regions. Pulsars emit radiation across a wide range of wavelengths, from radio to gamma rays. In intergalactic space, where electromagnetic fields are weak and plasma densities are minimal, These emissions can exhibit distinctive characteristics. The absence of surrounding plasma reduces dispersion and scattering, enabling cleaner and more precise measurements of the pulsar's signals. Additionally, the weak electromagnetic fields in voids may alter the pulsar's magnetosphere, subtly shifting the properties of its emissions. By comparing the emissions of isolated pulsars with those in denser regions, researchers can investigate how the surrounding environment shapes pulsar behavior. As isolated pulsars move through space, they interact with the intergalactic medium, leaving behind trails that reveal the magnetic structures of the regions they traverse. Pulsars generate powerful magnetic fields which can create shock waves and particle trails in the surrounding medium as they travel. These trails, often detectable in radio wavelengths, act as natural tracers for the distribution and strength of intergalactic magnetic fields. In cosmic voids, where magnetic fields are faint and poorly understood, pulsar trails provide a rare opportunity to map these otherwise invisible forces. These observations not only shed light on the magnetic environment of voids, but also offer insights into the evolution of magnetic fields on cosmic scales. Pulsars are very useful because they can last for a long time in low-energy settings. Pulsars interact with matter around them in galaxies and clusters, which speeds up the loss of energy and shortens their active lives. In the empty spaces between galaxies, these kinds of exchanges don't happen very often, so pulsars can keep their energy for a lot longer. Because they live so long, pulsars in gaps can keep working and be seen for millions or even billions of years. Astronomers learn about how neutron stars change over time by looking at these old pulsars. For example, they learn how their magnetic fields weaken and their spin rates slow down. Because they are so rare and far away, pulsars are great for understanding how very large pieces of stars interact with the vastness of space. Scientists can use their solo travels to learn more about how matter, magnetic fields, and energy are spread out in the world. For instance, how do the features of pulsars change in places where there isn't a lot of electromagnetic or gravitational interference? How do their tracks show the big picture of intergalactic space, such as whether dark matter or weak baryonic matter is present? Isolated pulsars can help answer these questions by being used as nature labs to study the physics of very harsh circumstances. Radio telescopes and X-ray detectors can pick up the faint signs of pulsars that are far away, even if they are very far away in space. These unusual objects will be easier to find and study with the help of future intergalactic projects like the Square Kilometre Array, SKA, and next-generation X-ray satellites. Researchers will be able to look into the spin-down rates, emission properties, and trails of individual pulsars in a way that has never been done before. Ghost light, diffuse radiation of the universe. This light fills the huge spaces between galaxies with a soft, hazy light. It is present in intergalactic space but not loud. Though it doesn't come from a single source, it is the effect of many processes and events happening in other galaxies. The dim glow from lost stars in other galaxies is one of the main sources of this ghost light. These stars were thrown out of their parent galaxies by strong gravity pulls. They now float alone in the vastness of space, their light mixing with the faint haze that covers the whole universe. Orphan stars are the castaways of the cosmos, often torn from their galaxies during galactic mergers or tidal interactions. When two galaxies collide or pass close to each other, the immense gravitational forces at play can rip stars from their orbits, flinging them into the intergalactic medium. These stars, unbound and isolated, continue to shine for billions of years. Individually, their light is too faint to detect, but collectively, they create a diffuse glow that adds a subtle luminescence to the intergalactic void. This orphan starlight is not just a byproduct of galactic interactions. It is a testament to the dynamic and ever-changing nature of the universe. Intracluster light, a soft glow that fills the gaps between galaxies in galaxy clusters, is another important source of ghost light. When galaxies crash into each other or join, Stars, gas and dust are stripped from them and left behind in the gravity well of the cluster. This is how intra-cluster light is formed. Because of these interactions, matter is spread out over very large areas, making a faint, ghostly light that goes all the way across the cluster. Intra-cluster light is like a fossil record of how galaxies used to interact with each other, giving us clues about how they formed and changed over time. Astronomers can piece together the events that formed these huge structures in space by studying this light. Ghost light is more than just a glow. It is a powerful tool for mapping unseen interactions and structures. The distribution and intensity of diffuse radiation provide a way to trace the gravitational forces that govern the universe. For instance, the patterns of intra-cluster light can reveal the influence of dark matter, the invisible substance that makes up the majority of the universe's mass. Dark matter does not emit or absorb light, but its gravitational pull shapes the distribution of stars and gas. By analyzing ghost light, scientists can indirectly map the presence of dark matter, gaining insights into the large-scale structure of the universe. Stripped stars, often referred to as the leftovers of galactic events, play a crucial role in creating diffuse radiation. These stars are the survivors of violent cosmic interactions, such as galactic collisions or tidal stripping, where entire swathes of stars are torn from their host galaxies. Stripped stars drift in intergalactic space, far from the dense environments where they were formed. Their faint light combines with that of other orphan stars to produce the ghostly glow observed in galaxy clusters and voids. These stars are not just relics of past events, but are also key to understanding the processes that govern galaxy formation and evolution. The task of finding diffuse radiation is difficult and needs advanced monitoring skills and cutting-edge tools. It's hard for regular telescopes to see this faint glow because galaxies and stars give off much brighter light that blocks it out. For astronomers to see ghost light better, they use special methods like deep sky photography and stacking multiple images. Observatories in space with very delicate instruments can pick up very dim light of all wavelengths, from visible to infrared. With these tools, scientists can look at the spectral features of diffuse radiation, which helps them figure out what the light is made of and where it comes from. The ghost light absorbed across vast deserts of space offers additional insights into the composition and history of the intergalactic medium. As light travels through these sparse regions, it interacts with the gas and dust scattered throughout the void. These interactions leave imprints on the light, altering its spectrum in ways that provide clues about the density, temperature, and composition of the intergalactic medium. By studying these absorption patterns, astronomers can reconstruct the history of these regions, tracing the processes that shaped them over billions of years. This connection between ghost light and the intergalactic medium underscores its importance as a probe for understanding cosmic evolution. The patterns of scattered radiation are not random, they show how the world is structured. The glow of intra-cluster light is stronger in dense galaxy clusters. This shows how the cluster's huge dark matter ring pulls on it. In comparison, the diffuse glow is weak and spread out in the huge spaces between the groups, making it clear that there are no important structures there. The cosmic web is the huge network of filaments and voids that make up the structure of the universe on a big scale. These designs are a picture of it. Ghost light follows this web and shines a light on the forces and processes that make its complex shape. Ghost light can also show us how stars and galaxies age and die. Diffuse radiation comes from a variety of star types, from young, huge stars that have been torn apart by galaxies to older, cooler stars that are still in intergalactic space. Astronomers can figure out the age, metallicity, and makeup of these stars by looking at the spectral features of ghost light. This helps to understand where these stars came from and how they evolved over time. Scientists can use this knowledge to learn more about how stars form, how galaxies interact, and how matter moves around in the world. The elusive warm-hot intergalactic medium. The warm-hot intergalactic medium, WIM, is one of the most mysterious parts of the universe. It fills the gaps between galaxies and clusters and stretches across huge cosmic strands. As baryonic matter moves between the cosmic medium and galaxies, it is in a liminal state, a time of change. The WIM is a layer of gas between the cool gas of the intergalactic medium and the hot plasma found in galaxy clusters. Its temperatures range from 10 to the power of 5 to 10 to the power of 7 Kelvin. This one-of-a-kind state of matter stores baryons, which makes it an important part of the flow of matter and energy in the universe. The WIM's low density contributes to weak gravitational lensing, a subtle distortion of light from background sources caused by its presence, while galaxy clusters and dense cosmic structures cause strong lensing effects. The WIM produces faint distortions that require advanced observational techniques to detect. These distortions allow astronomers to map the large-scale structure of WIM, revealing its distribution along cosmic filaments and its role in shaping the universe's framework. The ability to detect such weak lensing offers a window into the intricate interplay between light and matter in the universe's most diffuse regions. One thing about the WIM is that its chemical makeup changes over time. The WIM is made up of heavy elements like carbon, oxygen, and iron that are moved around by galaxy winds and supernova blasts. Over the course of billions of years, this movement has formed a changing chemical makeup that shows how galaxies work. Studying these elements in the WIM gives us a record of the chemical development of the universe. This helps us understand how matter is spread out and changed on a galactic scale. The WIM's link to galaxy groups shows how it acts as a link between different types of space objects. WIM filaments connect galaxies and clusters, letting cooler gas flow through them and changing the temperature of the medium inside the clusters. These relationships are very important for controlling the flow of matter into clusters, which in turn affects how big and stable they are. In some cases, the WIM causes instability on the edges of clusters, which changes how hot gas is accreted and could affect how fast stars are formed in galaxies. Additionally, magnetic fields inside WIM strands are an interesting topic. These weak but consistent magnetic fields line up along the cosmic web, which points to a beginning that is connected to the very beginning of the universe. As the WIM reacts with galaxy clusters and mergers, turbulent processes make these fields stronger. This makes a network of magnetized strands that affect how charged particles move. These fields give us important information about where cosmic magnetism came from and how it has changed over time. The WIM also plays a unique role in absorbing cosmic rays. Low-energy cosmic rays, which propagate through intergalactic space, encounter the WIM as a barrier, slowing their movement and affecting their energy. At the same time, the WIM may contribute to accelerating particles along its boundaries, creating distinctive emission signatures in X-ray and gamma-ray bands. These interactions provide insights into the dynamic relationship between intergalactic gas and high-energy particles. The WIM has marks from the reionization era, a time of change when the universe's first galaxies and stars charged the neutral hydrogen. There are faint ionization signatures from this time that can be seen in the WIM. These signatures show how this medium was heated and formed by the first light sources. These marks are like a record of the past. They link the WIM to the events that shaped the early development of the universe and the change from darkness to light. From time to time, the WIM is seen at the edges of cosmic gaps where strands meet. These thermal threads are very rarely seen, but they act as intermediate zones where the WIM meets cold void gases. These kinds of interactions make unique structures that are hard to see with regular tools, but necessary for understanding how cosmic strands and gaps interact with each other. It's possible that these heat bridges also let matter flow into bigger structures, which shows how important the WIM is to the cosmic cycle. Feedback from active galactic nuclei, AGN, and massive starbursts creates shockwaves that travel through the WIM, compressing gas and temporarily increasing its temperature and density. These feedback-induced shocks produce transient X-ray flares, observable on small scales, providing direct evidence of the WIMP's response to energetic cosmic events. Such shocks also influence the redistribution of matter and energy within the WIMP, shaping its structure and properties over time. In ultra-low density regions of the WIMP, quantum effects may become significant. At such low densities, the wave functions of particles can overlap, subtly altering their interactions. These quantum effects, while difficult to observe directly, could impact the WIMP's thermal properties and its role in transferring energy across cosmic scales. Understanding these effects requires innovative observational and theoretical approaches, bridging the gap between quantum mechanics and large-scale astrophysics. The WIMP is also linked to the growth of early black holes. Filaments near primordial black holes act as feeding channels, supplying ionized gas that sustains accretion processes. This flow of material may explain the existence of some unusually massive black holes in the early universe. Observing these interactions provides insights into how the WIMP contributes to the evolution of black holes and the larger structures that surround them. Gravitational waves traveling through the WIMP encounter unique conditions that slightly alter their propagation. The ionized gas in the WIMP can cause minute dispersion effects, creating measurable distortions in gravitational wave signals. These effects offer a new way to map the WIMP's structure and distribution, linking gravitational wave astronomy with the study of intergalactic gas. The WIMP also works with galaxy halos, taking gas out of them and moving matter between galaxies. These interactions control the rate at which stars are formed by either giving galaxies new stuff to work with or keeping them from getting the gas they need to keep making stars. There are cold streams of heavier gas hidden in the WIMP that can withstand shock heating. This gives pure material a direct way to fuel galaxy growth. These streams are hard to see, but they carry knowledge about the world in its earliest form that hasn't been changed. Void cascades, how smaller voids merge to create supervoids. Over billions of years, these empty spaces grow and get bigger until they join together to form bigger structures called supervoids. This process of joining, called void cascades, makes huge areas that are almost completely empty that stretch across hundreds of millions of light years. In contrast to denser cosmic structures that are made by gravity and crashes, voids change over time due to less visible and subtle forces. In the early universe, the first voids were areas where matter didn't gather because they weren't dense enough. These smaller holes were formed by differences in the spread of intergalactic gas in different areas, leaving clear areas of empty space. These areas didn't have as much gravitational pull as their heavier peers, so they didn't get much attention over cosmic timescales. As the universe grew over time, these holes started to get bigger, pushing outward and making bigger holes in the fabric of space. Differences in temperature pressure are one of the things that cause voids to expand. In voids, where there aren't many things around, gas is in a very unstable state because it doesn't connect with anything much to move heat or energy. Different levels of pressure make gaps get bigger and their edges stretch as gas moves outward from slightly heavier areas. When two growing voids touch, the border between them falls apart, letting them join together to form a single, bigger void. This process is usually not noticeable, but over billions of years, it changes the shape of space between galaxies. The collapse of void boundaries is a gradual process. Unlike the dramatic collisions seen in galaxy clusters, void mergers are marked by the slow erosion of separating walls. Gas and sparse intergalactic material flow between the two regions, smoothing the transition zone until the boundary effectively disappears. This creates a seamless supervoid, with no clear divisions to indicate where the smaller voids once existed. Even within supervoids, the remnants of smaller voids can persist as subvoids. These layered structures reflect the history of void cascades, where smaller pockets of emptiness remain embedded within the larger structure. Subvoids often exhibit slight variations in density or temperature, hinting at the conditions that existed before the merger. Advanced simulations and observational techniques have begun to detect these subvoids, providing a glimpse into the complex evolution of void interiors. At the interfaces where voids merge, faint shock waves can form. These shock waves are the result of subtle energy redistribution as gas and material from the boundaries interact. Unlike the high-energy shock waves observed in dense galactic environments, void shock waves are incredibly weak and spread thinly across vast distances. Despite their faintness, these shock waves leave imprints that can reveal details about the merging process and the physical conditions within the void. When smaller voids join together, they change how they work inside in big ways. The gaps change the way temperatures are distributed, which can lead to long-lasting cold zones. When there is no outside heat, these cold zones become some of the most safe places in the world. These temperatures have stayed the same for billions of years because no energy is being added and gases aren't interacting with each other much. Supervoids formed through void cascades rarely take on spherical shapes. Instead, their final structures are often irregular, reflecting the asymmetry of the merging process. The shapes of these voids are influenced by the initial orientations of the smaller voids, as well as the direction of their expansion. This irregular geometry creates unique challenges for astronomers trying to map these vast regions and understand their properties. Gas flows play a critical role in void cascades. The walls separating voids are gradually eroded as gas moves away from denser regions. Over time, this erosion weakens the boundaries, allowing the voids to merge. Sparse plasma streams within these regions also contribute to the process, smoothing out irregularities and helping to redistribute material across the void. Molecular reactions within voids are another fascinating aspect of their evolution. Even in the near vacuum of a void, trace amounts of gas can interact to form molecular hydrogen. These reactions occur at extremely slow rates, driven by the unique conditions of void interiors. The resulting molecules provide valuable insights into the chemistry of sparse regions, where interactions are rare but impactful. During the merging process, gas and other material can form residual streams connecting smaller voids within the larger supervoid. These streams are faint and difficult to detect, but serve as markers of the merging history. Observing these trails can help scientists reconstruct how voids evolved and how material was redistributed during the cascade. Void cascades also involve subtle shifts in energy. As gas and material move during the merging process, energy is redistributed across the expanding void. This redistribution creates low-energy zones within the supervoid, where conditions become even more stable and inert. These zones highlight the unique thermodynamic properties of void interiors, where energy exchange is minimal. The future of void cascades lies in their continued growth. As the universe expands, voids will become larger and more isolated, merging into even vaster supervoids. The process will slow over time as the remaining material becomes increasingly diffuse. The intriguing behavior of rogue stars. Rogue stars are interesting travelers through the universe. They get separated from their home galaxies by strong events that send them flying at very high speeds. A lot of these stars, which are also called hypervelocity stars, are on their way because of gravity slingshot effects that happen when they meet with dense stellar systems or massive black holes. When these things happen, they launch them through space at such high speeds that they can avoid the pull of both their home galaxies and galaxy groups. Rogue stars often have very fast spinning speeds because of the force of these events, making them spin much faster than usual. This fast spin can change the star's shape, making it oblate and more likely to have surface instability. Dual supermassive black holes, often formed during galactic mergers, are particularly efficient at ejecting rogue stars. When a star ventures too close to such a binary system, it can be flung away at hypervelocity speeds, potentially exceeding thousands of kilometers per second. This phenomenon, unique to the chaotic environments around merging galaxies, highlights the violent processes that shape the dynamics of rogue stars. These high-speed ejections often leave their mark, with stars showing altered chemical compositions or unusual spectral features. While rogue stars are typically solitary travelers, some manage to retain their companions, forming rare binary rogue systems. These pairs remain gravitationally bound even as they are ejected into intergalactic space. Such binary systems provide an intriguing glimpse into the dynamics of stellar ejections, as they must overcome incredible forces to remain intact. The dynamics of these pairs, including their orbits and relative velocities, offer critical data on the mechanics of their ejection and the environments they passed through. As rogue stars traverse intergalactic space, their interactions with the surrounding medium can leave subtle yet detectable marks. Sparse intergalactic gas may strip material from the stars, creating unique spectral features that differ from those of stars within galaxies. These stripped atmospheres tell a story of isolation, shaped by the slow erosion of material as the stars journey through the void. Some rogue stars may also carry with them remnants of their galactic origins, such as gas nebulae ejected alongside them. These isolated stellar nurseries float through space, acting as miniature ecosystems where new stars might form under the right conditions. Rogue stars that come from dwarf galaxies that have been damaged give us a unique look into the chemistry past of the universe. A lot of the time, these stars have unique signs that come from their parent dwarf galaxies, which are chemically different from bigger systems. Their makeup, which includes more or less certain elements, tells us about the places where they formed. Astronomers can piece together how dwarf galaxies die and what they add to the intergalactic medium by studying these stars. Some rogue stars act as time capsules, preserving evidence of ancient galactic collisions. Their velocities and trajectories can be traced back billions of years, revealing the locations and nature of past cosmic interactions. These stars, displaced by events long since concluded, provide a rare opportunity to reconstruct the history of the universe's most dramatic mergers and tidal disruptions. This historical value is further enhanced when clusters of rogue stars are found drifting together, remnants of galaxies or star clusters torn apart by larger gravitational forces. Some rogue stars are not like everyone else. When neutron stars or pulsars are thrown into intergalactic space by supernovae interacting, they send out strong X-rays or gamma rays that can be seen from very far away. These rogue pulsars leave behind electromagnetic trails that light up the space around them like lanterns in the universe. These trails, which are often visible in radio waves, tell us a lot about the cosmic medium's mass and makeup. Researchers can study parts of space that would be impossible to reach without these leaks. The movement of rogue stars through intergalactic space can also seed their surroundings with heavy elements. During their lifetimes, these stars eject material through stellar winds or, in their deaths, through supernova explosions. These processes enrich the surrounding intergalactic medium, creating localized pockets of heavier elements that may influence future star formation. This enrichment process makes rogue stars vital contributors to the chemical evolution of the universe, extending their influence far beyond their isolated journeys. An extremely unusual occurrence linked to rogue stars is the so-called double escape. Not only are these stars expelled from their home galaxies, but they are also expelled from their local stellar groupings. Stars with complicated dynamics necessary for dual ejection have histories and paths that are unlike any other. Examining these stars provides insight into the multi-scale processes of gravitational interaction, spanning from close collisions between stars to the dynamics of the galaxy as a whole. The dynamics of star-planet systems also undergo dramatic shifts when rogue stars are ejected. Planets orbiting rogue stars experience altered gravitational forces as they leave their galactic environments. This can lead to extreme orbital changes, including highly elongated orbits, or in some cases, stable configurations unaffected by external influences. These rogue planetary systems are intriguing laboratories for studying planetary evolution, under conditions vastly different from those within galaxies. Light echoes can be caused by rogue stars moving through gas clouds or reacting with galaxies close by. These echoes, which are light reflections from the star's past contacts, carry information about the star's path, speed, and qualities. Astronomers can figure out how rogue stars have been moving through intergalactic space for millions of years by looking at light echoes. Due to their very fast exit speeds, some rogue stars may show strange relativistic effects. Because these stars are moving at very small amounts of the speed of light, relativistic effects could cause changes in their colors and brightness. These effects give us a one-of-a-kind chance to look at how stellar dynamics combine with relativistic physics. They give us a rare look into where general relativity and astronomy meet. Clusters of rogue stars in intergalactic space might even represent the remnants of long-lost galaxies. These clusters, stripped of their galactic cores, drift through the void as ghosts of systems that no longer exist. The near-perfect emptiness of the Bootes void. The Bootes void is a huge empty space in space that is about 330 million light-years across. The nickname, the Great Nothing, comes from the fact that it is almost completely empty. It has many fewer galaxies than you would expect for an area of its size. Early views suggested it had no matter at all, but later research showed it had a few scattered galaxies. So it wasn't really a void, but more of an oddity, with few people living in it. People often call these galaxies galactic fossils. They are thought to be leftovers from a time when the void wasn't as empty. Because they are so far away, they have unique qualities that were formed by being so alone. Simulations suggest the Bootes void may have formed from disrupted cosmic filaments during the early stages of the universe's evolution. As gravity pulled matter into surrounding regions, the void was left behind, drained of its material over billions of years. This disruption may have been more severe than in other voids, creating an abnormally large and underdense region. The edges of the Bootes void are particularly intriguing, as they host clusters of galaxies forming faint shells. These shells likely mark the boundary where gravitational forces of nearby filaments halted the outward flow of material, creating a thin wall of galaxies encircling the emptiness. Within the Bootes void itself, there may still be hidden features waiting to be discovered. Sparse cold gas trails are theorized to exist in the region, remnants of incomplete gas flows that were not fully evacuated during the void's formation. These trails are incredibly faint and difficult to detect, but they could offer invaluable insights into the behavior of baryonic matter in ultra-low density environments. If confirmed, these gas structures might provide clues about the processes that shape the void and its interaction with nearby cosmic filaments. The few galaxies that do reside within the Bootes void exhibit unusual characteristics. Their isolation means they have experienced far fewer interactions, mergers, or external gas inflows than galaxies in denser regions. This isolation influences their star populations, with many of these galaxies showing a higher prevalence of low metallicity stars. These stars, containing fewer heavy elements, suggest that the galaxies have had limited opportunities for chemical enrichment, a process typically driven by interactions with neighboring systems. Their lack of interaction also results in remarkably stable morphologies, as these galaxies are free from the tidal forces and collisions that often reshape galaxies in more crowded regions. Dwarf galaxies may also be hiding in the Bootes void because they are so dim. It is extremely hard to find these small systems, especially in areas with few people, but their presence could tell us a lot about how stars grow and how people survive in very remote areas. If these galaxies are found, they would be some of the cleanest places in the universe. They would give us a unique chance to see how galaxies form in almost complete isolation. Unlike denser regions, where matter tends to flow symmetrically toward massive structures, the Bootes void disrupts this flow. Surrounding matter is drawn toward nearby filaments and clusters rather than through the void, creating asymmetrical flow patterns that challenge standard models of large-scale cosmic motion. These unique dynamics underscore the role of voids like Bootes in the delicate balance of the cosmic web. Even galaxies in the void move in strange ways. Their tracks seem to be separate from the bigger cosmic flows because they are not affected as much by gravitational interactions with nearby systems. Looking at these movements gives us secondary proof of how gravity works in places where there is almost no matter at all, which is where normal theories of gravity fail. The Bootes void's extreme emptiness also affects the electromagnetic environment. The lack of surrounding gas and plasma means that void galaxies produce significantly less radio and X-ray emissions compared to their counterparts in denser regions. This lack of signal creates challenges for astronomers attempting to study the region, but also provides an ideal environment for testing intergalactic electromagnetic phenomena without interference from brighter sources. The Bootes void's size and uniform emptiness suggest it may have formed from the coalescence of smaller voids over billions of years. This supervoid formation process may still be ongoing, with the void continuing to reshape its boundaries and affect the surrounding cosmic structure. The gradual merging of smaller voids into the Bootes void highlights the dynamic nature of the cosmic web and the forces that govern its evolution. Some ideas say that the Bootes void might be the remains of a primordial bubble that formed when the universe was expanding very quickly. If this is true, the void would have qualities that are very different from those of other cosmic gaps. This would give us a unique look into the early stages of cosmic inflation. Due to their low density, sparse gas clouds in the void may also have slower star formation. This makes them some of the least processed matter in the universe. These clouds might hold information about the world when it was first created, giving us a unique look at what things were like right after the Big Bang. Their appearance makes the Bootes void even more interesting as a natural laboratory for studying the beginning stages of how the universe formed. It is thought that the cosmic medium in the Bootes void is one of the coldest places in the universe that we can see. Since there isn't much in the gap to hold or move heat, the temperature drops to levels that are rarely seen anywhere else. There are new questions about how heat and energy are spread in the universe because of this very cold climate that tests current models of thermal equilibrium in intergalactic space. The Bootes void's emptiness creates a unique cosmic silence, free from the electromagnetic noise of active galaxies or dense clusters. This makes it an unparalleled location for detecting faint intergalactic signals, such as hypothetical axion interactions or weak gravitational waves. The void's isolation offers an unparalleled setting for testing fundamental physics in a region almost entirely devoid of matter. There may also be rogue black holes in the Bootes void. These could be the remains of old dwarf galaxies or black holes that were pushed from close systems. As they move through intergalactic space, these black holes may be some of the universe's most isolated singularities. Keeping an eye on their effects, like gravitational lensing or weak X-ray rays, could help us understand how black holes behave when they are very far away from each other. Primordial density fluctuations. The universe's oldest traces are primordial density fluctuations, which are small changes in the density of matter that came from the quantum fabric of the universe during the inflationary era. At first, these changes were quantum perturbations, which are tiny ripples in spacetime that quickly grew to cosmic proportions as the early universe expanded at an exponential rate. These waves turned into the building blocks of the universe's structure when inflation stopped. They made galaxies and the huge gaps between them possible. The self-amplifying nature of gravity played a critical role in the evolution of these fluctuations. Slightly denser regions acted as gravitational wells, drawing in more material over time. This process amplified their density, creating a feedback loop where mass gathered more mass, accelerating the formation of cosmic structures. These self-reinforcing wells grew to form the nodes of what would eventually become the cosmic web, the intricate network of filaments and voids that defines the universe today. The patterns of these density fluctuations were far from random. They formed interference patterns in the primordial plasma, with areas of constructive interference creating dense peaks and destructive interference forming vast, underdense troughs. These wave-like patterns were shaped by the interaction of sound waves traveling through the hot plasma of the early universe, imprinting oscillatory structures onto the distribution of matter. These changes were made even more complicated by the chaos in the early universe. Chaos in the initial plasma caused the density distribution to become less even as it swirled with energy. Even though this turbulence was very small, it caused localized problems that were different from what standard inflation models indicated, which were smoother, wave-like patterns. These flaws left their own marks that would later affect how galaxies and clusters formed. Primordial density fluctuations are also linked to the origins of magnetic fields. The slight differences in density during the universe's earliest moments may have seeded weak magnetic fields, which were later amplified by gravitational interactions and cosmic flows. These primordial magnetic fields played a role in shaping the dynamics of matter as it coalesced into stars and galaxies. In regions where density peaks were exceptionally high, the universe experienced rare collapses that led to the formation of high-density singularities. These singularities could have evolved into primordial black holes, compact objects that may still exist today as relics of the early universe. Unlike black holes formed by the collapse of stars, these primordial black holes would have emerged directly from the gravitational collapse of extreme density fluctuations, bypassing the need for stellar evolution. Phase transitions in the early universe created defects such as cosmic strings or domain walls, which could have subtly altered the distribution of matter. These defects acted as gravitational anomalies, bending the surrounding density patterns and creating irregularities that deviated from purely inflation-driven fluctuations. A lot of the tiny changes in density were smoothed out by heat movement in the primordial plasma. In the early moments after inflation, shock waves and changes in the spread of energy removed smaller details, leaving only bigger, stronger patterns. This stopping of small-scale changes created a cutoff in the range of density changes, which successfully filtered out noise and kept the universe's overall structure. Fluctuations also gave rise to plasma voids, regions where the density was so low that material could not clump together to form structures. These voids acted as empty pockets in the early universe, surrounded by denser regions that continued to draw in matter. These plasma voids represent some of the earliest instances of structural contrast in the cosmos, precursors to the vast cosmic voids we observe today. Rare collapse-triggered streams emerged in high-density regions, where material falling into gravitational wells created dynamic flows that redistributed matter across vast distances. These streams influenced the surrounding density troughs, carving out patterns in the plasma that would later shape the cosmic web. These flows were among the earliest examples of matter movement driven by gravitational gradients, providing a glimpse into the dynamic processes that continue to shape the universe. The causes of these changes make their quantum nature clear. The wave function breakdown of the inflaton field, the hypothetical scalar field that caused inflation, was a key part of creating small imbalances in the early universe. Even though these differences were small, they caused flaws that would later be made worse by gravity forces. Scalar fields beyond the inflation also contributed to the formation of density fluctuations. Secondary scalar fields, arising as quantum corrections to inflation, created interference patterns that modified the density distribution. These patterns added complexity to the fluctuations, making them more intricate than what simple inflationary models predict. The symmetry-breaking processes during inflation shaped the scale-dependent nature of these fluctuations. Small deviations from perfect symmetry in the inflaton field influenced how density variations were distributed across different scales. This fine-tuning of initial conditions created a more detailed structure than previously understood, introducing features that challenge standard cosmological models. Energy dissipation events occurred in localized regions of extreme density, where the rapid scattering of waves reduced some fluctuations and enhanced others. These energy redistributions left imprints on the density field, creating patterns that deviated from purely gravitational influences. These dissipation events highlight the dynamic interplay of forces in the early universe, where gravity, pressure, and quantum effects worked together to shape the cosmos. The most extreme density peaks accelerated early cosmic evolution by acting as gravitational accelerators. These regions drew in material at a faster rate, creating the first gravitational sinks that shaped the overall pace of structure formation. Their influence extended beyond their immediate surroundings, subtly shaping the evolution of nearby regions. The early universe's density fluctuations also reveal evidence of pre-inflation processes. Anomalies in the fluctuation spectrum suggest that physical events preceding inflation, such as energy transitions in the inflaton field, left faint imprints. These anomalies challenge the notion that inflation erased all pre-existing conditions, instead hinting at a more complex pre-inflationary era. Changes in the universe's plasma were also affected by fluctuations. Differences in pressure in the primordial plasma caused shock waves that changed the distribution of energy and density, making the surface even less smooth. Before the plasma slowed down, these waves set off larger-scale movements that changed how the matter was spread out. Some theories say that the big and small changes in density could be caused by interactions between scalar fields and quantum entanglement effects. It's possible that these interactions linked faraway parts of the universe, leaving behind minor patterns that can still be seen in the structure of the universe today. Quantum entanglement gives us an interesting look at how the conditions at the start of the world are linked on very large scales. The cosmic desert. Intergalactic gas anomalies in cosmic deserts give us interesting information about how matter behaves when there isn't much of it. Gas flows through these areas aren't always steady, and some places have cold gas pockets that won't fall. Because these are intergalactic gas anomalies, as are not affected by the gravity pull of nearby filaments and clusters, they stay in a nearly static state. This shows how matter acts when there aren't many outside forces acting on it. The fact that these cold gas trails are still there suggests that there was action in the early universe, when initial flows did not fully clear some areas. Star formation in cosmic deserts is practically non-existent. These regions are often referred to as starvation zones due to the lack of the necessary ingredients for stellar birth. Gas densities in deserts are far too low to trigger gravitational collapse, and without sufficient external pressures or shocks, the material remains diffuse. This absence of star formation creates an environment where evolution slows to a crawl, leaving deserts as static, unevolving regions over cosmic timescales. Occasionally, sparse intergalactic dust clouds are found drifting through the depths of cosmic deserts. These clouds are anomalies, as their survival in such barren environments raises questions about their origins and stability. Without the gravitational protection of galaxies, these dust clouds exist in precarious isolation, subject to dispersal by weak intergalactic forces. Their composition often reflects a lack of interaction with stars, containing fewer heavy elements, and showcasing a primordial chemical makeup. Cosmic deserts play a significant role in shaping the boundaries. The gravitational emptiness of deserts limits the connectivity of surrounding filaments and clusters, creating natural gaps in the web structure. These regions act as buffers, slowing the transfer of matter and energy between dense regions. The gravitational effects of deserts extend to nearby structures, subtly influencing the motion of galaxies and the flow of intergalactic gas. Fossil evidence of ancient matter dispersal can be found in deserts, revealing the remnants of early cosmic flows. Traces of gas and debris, left behind by primordial gravitational forces, create faint imprints that serve as a record of the universe's formative years. These patterns reflect the dynamics of matter redistribution billions of years ago, providing clues about the processes that sculpted the universe's architecture. Unlike the gas in dense regions, which undergoes constant recycling through stellar processes, the material in cosmic deserts remains untouched by heavy element enrichment. As a result, it often retains a pristine composition, containing primarily hydrogen and helium, with minimal traces of heavier elements. Studying this unprocessed material offers a rare opportunity to understand the elemental conditions of the early universe. In some parts of cosmic deserts, the gas reaches a state of thermal equilibrium, maintaining consistent temperatures over extended periods. These regions exhibit little to no temperature variation, as the sparse matter lacks the interactions necessary to generate significant energy transfers. This thermal stability provides a natural laboratory for studying the behavior of gas in near-static conditions, where external influences are negligible. Gaps in the cosmic web's connections are caused by cosmic deserts, which change how matter moves between strands. These gaps are natural barriers that send cosmic gas in different directions and stop it from moving over long distances. The resulting split can change the supply of raw materials for growth, which can affect how galaxies and clusters grow. These deserts break the flow of space and time in a way that makes the uneven spread of matter in the universe stand out. At the edges of deserts, isolated star clusters can sometimes be found, clinging to the boundaries where filaments meet the barren expanses. These clusters, existing on the fringes of cosmic emptiness, evolve slowly due to their isolation from external gravitational forces. Without the frequent mergers or interactions that drive change in denser regions, these clusters retain their original characteristics, acting as snapshots of a bygone era. Deep within the deserts, hidden nebulae occasionally emerge, detectable only through faint emissions. These nebulae are remnants of isolated intergalactic material, slowly dissipating without the pressure or shock waves necessary to collapse into stars. Their faint light offers a glimpse into the conditions of intergalactic gas in these barren regions, where the forces of gravity and radiation are too weak to significantly shape their structure. The lack of interference from dense environments allows for the observation of phenomena that are otherwise obscured. Exotic interactions between particles, such as weakly interacting neutrinos or rare decay events, can occur in these ultra-quiet regions, offering new opportunities to test theories of fundamental physics. Occasionally, material trails left by ancient galactic collisions are found stretching through cosmic deserts. These sparse remnants of early interactions create faint lines of debris that connect otherwise isolated regions. These trails serve as evidence of a more dynamic past, where the movement of galaxies and intergalactic flows left subtle imprints on the desert's emptiness. Galaxies in cosmic deserts are trapped in time, and their evolution happens on very different timescales than that of galaxies in thicker areas. Because they aren't affected by gravity forces or interactions from outside sources, they grow more slowly and keep their original qualities. This separation from time creates galaxies that look like they have frozen in time, giving us a unique chance to study how galaxies behaved in the past. Within the depths of cosmic deserts, primordial void pockets may exist, representing some of the emptiest known regions of space. These ultra-low density areas are remnants of early gravitational instabilities that failed to coalesce into more structured regions. Their emptiness serves as a stark contrast to the bustling activity of filaments and clusters, underscoring the universe's vast diversity. Sometimes, very rare intergalactic waves can cross deserts and connect groups and strands that are far away. These weak tide forces change the movement of sparse matter in very small ways, making flow patterns that are hard to see. These tides show that deserts are alive and changing, even in the most empty areas, where the weight of bigger buildings changes the shape of the ground. Gas flows at the boundaries of deserts often encounter redirection or stagnation, creating unique transition zones. These interactions define the edges of deserts, where material from denser regions encounters the near emptiness of the barren expanse. These boundary zones act as a buffer, moderating the flow of matter and energy between contrasting regions. Void resonance: how emptiness amplifies universal vibrations. Void resonance is one of the universe's least known phenomena. Unlike dense areas packed with galaxies, stars, and gas, voids are vast stretches of near-total nothingness that allow unique oscillations and vibrations to exist unhindered. These zones, which may span hundreds of millions of light-years, operate as amplifiers for cosmic occurrences, sustaining waves and vibrations that would otherwise evaporate in denser surroundings. The immense size of voids allows long-wavelength oscillations to persist. In dense regions, waves encounter obstacles that scatter and dampen them, but voids lack these interferences. This makes voids ideal for the amplification of phenomena like primordial oscillations that stretch across vast cosmic distances. These oscillations, originating from the early universe, are faint but detectable in the emptiest regions, offering a glimpse into the dynamics of the cosmos when it was just beginning to form. Light traveling through voids experiences unique interactions due to the near absence of matter. Photon trajectories are subtly influenced by the emptiness, allowing coherent light waves to maintain their properties over greater distances. This lack of scattering or absorption amplifies certain characteristics of the light, creating patterns that reveal the structure of the void itself. These amplified trajectories also make voids useful for studying how light behaves in low-density environments, free from the distortions caused by gravitational wells or dense gas clouds. Within voids, subthermal oscillations in the sparse intergalactic gas create faint vibrations. These oscillations, driven by minimal thermal fluctuations, occur because the sparse gas lacks the density required for efficient energy dissipation. As a result, the gas vibrates in low-frequency modes, creating a resonant hum that persists across the void. These oscillations, though subtle, provide valuable insights into the physical conditions of void interiors, where even the faintest movements can propagate over large distances. The boundaries of voids are particularly dynamic regions. At these edges, where the density transitions between the void and surrounding filaments, oscillatory effects are often amplified. These boundary zones act as natural amplifiers, reflecting waves back into the void interior. This process creates a whispering gallery effect, where oscillations are confined along the boundary, reinforcing their intensity. This phenomenon is similar to how sound waves behave in architectural structures designed to enhance acoustics, like the domes of whispering galleries. In the vastness of voids, weak plasma streams can produce unusual wave patterns. These ultra-thin streams, which are frequently leftovers of intergalactic flows, produce low-frequency oscillations as a result of particle interactions. Unlike dense plasmas, which are extremely active and turbulent, plasma in voids is quiescent, allowing waves to flow with little resistance. These oscillations expose the plasma's physical parameters like density, temperature, and composition, giving researchers a unique opportunity to investigate intergalactic matter in isolation. Void resonance also preserves vibrations from ancient cosmic flows. These fossil waves are relics of the early universe's energy distribution, preserved in the near-static environment of voids. Unlike dense regions, where waves are quickly absorbed or scattered, voids act as storage zones for these oscillations, allowing them to persist for billions of years. These preserved waves carry information about the initial conditions of the universe, offering clues about how matter and energy were distributed in the primordial cosmos. Rarefied shock waves passing through voids have unique amplification qualities. As these waves travel through the sparse cosmic medium, they find less resistance, allowing their energy to be preserved across extended distances. This amplification mechanism sheds light on the dynamics of energy transmission in low-density systems, where even little shock waves may have a substantial influence over time. Localized microresonances occur within sub-regions of voids, where slight variations in density create hotspots for wave amplification. These microresonances are analogous to the standing waves observed in musical instruments, where certain frequencies are naturally reinforced. In voids, these resonances can influence the movement of particles and the distribution of energy within these subregions, creating localized phenomena that differ from the overall void environment. Gas flows within voids diverge rather than converge, creating unique resonant patterns. Unlike the flows in dense regions, where gravitational forces draw matter together, void flows are driven apart by the absence of significant gravitational pull. This divergence creates a self-sustaining oscillatory pattern, as the movement of gas reinforces itself in the empty expanse. These patterns are particularly valuable for understanding how matter behaves in environments where gravitational influences are minimal. Void resonance depends on void geometry. The form and size of a vacuum dictate its resonance frequencies, much the way a drum or room's proportions impact its sound. Intergalactic gas pulses interacting with this geometry cause particular vibration patterns that indicate the void's structure. These interactions are essential for investigating void structure and evolution. Pressure waves traveling through the sparse intergalactic medium in voids create periodic vibrations that are invisible in denser regions. These waves, generated by faint interactions between particles, propagate across the void, revealing details about the physical state of the medium. The unique conditions within voids allow these waves to persist longer and travel farther than in more crowded environments. Molecular oscillations within void gases also occur, despite the extreme sparsity of matter. Trace molecules interact in ways that generate subtle oscillatory behaviors, providing a unique setting for studying chemical dynamics in near-vacuum conditions. These rare interactions could offer insights into how molecules behave in environments far removed from the conditions of stars or galaxies. Void resonance aligns wavefronts across huge cosmic distances, providing coherent oscillations measurable by advanced observational methods. Void emptiness lowers interference, allowing waves to move without losing coherence. This phenomenon helps investigate phenomena with extended observational baselines. Time and relativity in the cosmos. In the early 20th century, Albert Einstein's theory of general relativity overturned centuries of scientific thought. Before Einstein, time and space were considered immutable, fixed backdrops against which the universe played out its dramas. Newtonian mechanics held sway, treating time as a universal constant and space as an unchanging arena. But Einstein's insights revealed a deeper truth. Space and time are not separate entities, but intertwined into a four-dimensional continuum known as space-time. This revolutionary concept forever altered the way we perceive the cosmos. The essence of general relativity lies in the idea that massive objects warp space-time. Picture a trampoline with a heavy ball placed in the center. The surface bends around the ball, and smaller objects placed on the trampoline roll toward it. Similarly, in space-time, massive objects like stars create curvature, influencing the paths of nearby objects. This curvature manifests as gravity, drawing planets into orbit and guiding galaxies along their trajectories. Gravity, therefore, is not a force acting at a distance, as Newton proposed, but the result of space-time's curvature. Time dilation, the phenomena wherein the velocity of an object and the force of gravity both affect the pace at which time passes, is one of the most remarkable outcomes of general relativity. Near a black hole or other area of strong gravitational attraction, time seems to stand still compared to an observer further away. A prominent example of this phenomenon, gravitational time dilation, was shown in the film Interstellar, in which astronauts close to a huge black hole seem to live through hours, while others further away seem to live through years. This portrayal, however dramatic, is based on actual physical principles. Additionally, relativistic speeds, those very close to the speed of light, cause time dilation. When an item's speed rises in comparison to a stationary observer, time slows down for the object in question, as stated in Einstein's special theory of relativity. Experiments with high-speed particles and precision atomic clocks mounted on fast-moving airplanes have verified this phenomenon. Time will seem very different to space travelers of the future when they journey to faraway stars at nearly the speed of light. A sad and contradictory dynamic is therefore created. Even if they only aged a few years, visitors may return to Earth and discover that decades have passed. The interplay of time and relativity becomes even more fascinating in the context of black holes. These enigmatic objects, with their immense gravitational pull, warp space-time to extremes. Near the event horizon, the boundary beyond which nothing can escape, not even light, time essentially comes to a standstill for an outside observer. For an individual falling into a black hole, however, time would seem to pass normally, even as their surroundings stretch and distort. This duality exemplifies the strange and counterintuitive nature of relativity. Space-time curvature also shapes the vast cosmic voids that dominate the universe. These underdense regions, where gravity is weak and matter is sparse, provide a stark contrast to the dense clusters of galaxies and the warped zones near massive objects. In these voids, space-time stretches relatively unimpeded, allowing light to travel vast distances with minimal distortion. The emptiness of these regions highlights the dynamic nature of space-time, which can expand, contract, and curve in response to the distribution of matter and energy. The relationship between space-time curvature and the cosmic void is central to our understanding of the universe's large-scale structure. General relativity predicts that the distribution of matter and energy shapes the universe's geometry. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, reveal subtle fluctuations in temperature that correspond to variations in space-time curvature. These fluctuations seeded the formation of galaxies and cosmic filaments, with gravity amplifying their growth over billions of years. Doubts regarding the very definition of time emerge as our cosmic exploration progresses. Does the passage of time proceed in a straight line, from the past to the future? Or does it fit into a four-dimensional block universe, where the past, present, and future all live side by side? In the block universe idea, which is backed by relativity, time is portrayed as a static dimension, similar to spatial dimensions, rather than a moving phenomenon. This theory states that the way our minds interpret events gives rise to the illusion of passing time. Such philosophical implications of time challenge our understanding of existence and causality. If all moments in time are equally real, what does this mean for free will and the nature of choice? Are we merely observers, traveling along a predetermined path? Or is there room for spontaneity and agency? These questions, while speculative, underscore the profound intersection of physics and philosophy in exploring the nature of reality. Future experiments and technologies promise to shed light on the fabric of space-time and the mysteries of time. Gravitational wave observatories, such as LIGO and Virgo, have already opened a new window into the universe, detecting ripples in space-time caused by the collision of massive objects. These waves, predicted by Einstein a century ago, provide direct evidence of spacetime's dynamic nature and offer insights into extreme events like black hole mergers and neutron star collisions. Space-based observatories such as the upcoming Laser Interferometer Space Antenna, LISA, aim to detect low-frequency gravitational waves, providing a broader view of spacetime dynamics. Meanwhile, experiments in particle accelerators and quantum laboratories explore time symmetry and the arrow of time, probing why time seems to flow in one direction, despite the symmetric laws of physics. These efforts may uncover new principles governing the evolution of the universe. Time is also very important to the deepest questions in physics. The finding of cosmic acceleration, which is caused by dark energy, says that the universe will keep expanding forever, with galaxies moving farther away from each other. This makes me wonder what will happen to time in the end. Will it go on forever, getting weaker as the world gets closer to a state of permanent emptiness? Or will something unexpected change the path of space-time, starting a new stage in the growth of the universe? Void erosion. Are voids sculpted by cosmic winds? Active galactic nuclei, AGN, play a critical role in shaping void boundaries. AGN-driven winds, fueled by supermassive black holes in galaxy centers, expel enormous amounts of energy and matter into intergalactic space. These winds extend far beyond the galaxies themselves, reaching the edges of voids. As they encounter sparse gas near the void boundaries, they sweep away residual material, smoothing irregularities and expanding the void's reach. Shockwaves from galaxy collisions and supernova events also propagate into voids, contributing to their erosion. These shockwaves carry kinetic energy that can dislodge and disperse faint gas clouds within voids. Unlike in dense regions, where shockwaves are absorbed or redirected by surrounding matter, voids offer minimal resistance, allowing these waves to travel further and sculpt the sparse material they encounter. Over time, these interactions contribute to the void's smoother, more homogeneous interior. Different levels of temperature in the gas between galaxies make thermal winds that push matter into or across the borders of voids. In places close to galaxy groups or starburst galaxies, the intense heat causes changes in pressure that push gas outward. These thermal winds reach into empty spaces and move around gas that isn't dense, making the already low-density core even less dense. This slow but steady process makes the void smoother over time, making the differences between the void's nothingness and the filaments around it even stronger. The gravitational pull of nearby filaments also plays a significant role in void erosion. Dense filaments, which form the backbone of the cosmic web, act as gravitational anchors, drawing in stray matter from void boundaries. This peeling away of material creates a gradual expansion of the void as it loses its remaining gas and faint structures to the more massive filaments. The interplay between voids and filaments highlights the dynamic nature of the cosmic web, where even the emptiest regions are constantly reshaped by their denser neighbors. Plasma streams, remnants of ancient intergalactic flows, act like cosmic sandpaper within voids. These ultra-thin streams contain sparse, charged particles that interact with residual gas, dispersing it over time. Unlike dense plasmas, which exhibit turbulence and strong interactions, the plasma in voids is quiescent, allowing subtle long-term processes to dominate. These interactions slowly erode any faint gas clumps or primordial remnants, leaving the void increasingly empty. Void interiors are also subject to entropy-driven erosion. In these ultra-low-density environments, matter naturally disperses as entropy increases, leading to a gradual smoothing of irregularities. This process is not driven by external forces, but rather by the inherent thermodynamic tendencies of the universe. Over billions of years, this entropy-driven evolution contributes to the void's homogeneity. Tidal forces at void boundaries, generated by nearby galaxy clusters and filaments, stretch and reshape the edges of voids. These forces create asymmetries, as some parts of the void are pulled more strongly than others. Over time, this stretching refines the void's shape, making it less spherical and more irregular. These tidal interactions reveal the interconnected nature of the cosmic web, where voids are not isolated but are instead influenced by the dynamics of their surroundings. The sparse gas inside gaps goes through slow chemical diffusion, which helps improve the void. Elements that are heavier tend to move to the edges, leaving the space inside simpler and cleaner chemically. This diffusion process only happens in gaps, where there aren't many gravity interactions, so elements can separate over very long periods of time. Shear forces within the cosmic web introduce further distortions to void shapes. Large-scale gravitational interactions create stress along void boundaries, causing them to elongate or fragment. These shear forces act as invisible sculptors, continuously modifying void geometry and influencing the distribution of sparse intergalactic matter. In the void cores, rarefied gas occasionally undergoes instabilities that lead to its expulsion. These instabilities, while subtle, create faint outflows that deplete the void interior even further. This process ensures that void cores remain some of the most pristine and undisturbed regions of the universe, free from even the faintest traces of intergalactic gas. Primordial flows from the early universe also left their mark on voids. These flows, which failed to fully evacuate certain regions, created faint gas trails and density anomalies that are slowly eroded by intergalactic forces. Over time, these residual patterns are smoothed out, leaving behind a more uniform void. Star formation near void boundaries introduces faint feedback winds that extend into the void. The energy released by forming stars, including stellar winds and supernovae, contributes to the redistribution of gas along the void edges. While this effect is minimal compared to AGN winds or shock waves, it still plays a role in shaping the transition zones between voids and denser regions. Void fusion, where smaller voids merge into larger ones, also contributes to void erosion. During the merging process, the boundaries of the smaller voids are disrupted, leading to the redistribution of gas and matter. This erosion ensures that the resulting larger void is smoother and more homogeneous than its predecessors. Even within voids, occasional gas particle collisions create subtle energy transfers that influence the distribution of matter. These rare interactions, though sparse, contribute to the long-term dispersal of gas, ensuring that any residual structures within the void are gradually smoothed out. Gravitational instabilities near void boundaries amplify the erosion process. These instabilities, caused by uneven mass distribution in nearby filaments or clusters, create localized gravitational pulls that strip material from void edges. Over time, these effects refine the shape of the void, contributing to its dynamic evolution. Pressure variations across void boundaries can create subvoid regions within larger voids. These subvoids represent pockets of even lower density, formed as pressure differences redistribute the sparse matter within the void. This process adds complexity to void interiors, creating layered structures within the emptiness. Low-frequency waves traveling through voids interact with the residual matter, creating faint ripples that redistribute gas. These interactions, while subtle, act over vast distances, slowly shaping the void's internal structure. The emptiness of voids allows these waves to travel unimpeded, amplifying their effects. Tiny clumps of matter or gas within voids are gradually evaporated by thermal and dynamic processes. These microstructures, remnants of the void's formation, are eroded over time, ensuring that the void becomes progressively emptier. This evaporation process highlights the delicate balance of forces within void interiors. Missing galactic satellites in sparse regions. Potential satellite galaxies in sparse regions face significant challenges from the very beginning. Inertia-dominated halos, which exist in such low-density environments, struggle to condense into visible structures. Without external gravitational interactions to perturb or compress the material, these halos remain diffuse, never reaching the density required for gravitational binding. This results in gas clouds that simply drift through intergalactic space without forming stars or compact structures. Thermal energy in sparse regions poses another barrier to satellite formation. Elevated temperatures in the thin intergalactic medium prevent gas within low-mass halos from cooling effectively. Cooling is essential for gas to collapse under gravity and form stars, but in sparse regions, thermal energy disrupts this process. Instead of coalescing into a galaxy, the gas remains suspended in a state of equilibrium, failing to transition into a satellite system. Void expansion amplifies these effects, filtering gas and dispersing material before it can accumulate into satellite galaxies. In these regions, gas flows become diluted as voids expand, creating conditions where the density of available material drops below the threshold for star formation. This process not only prevents new satellites from forming, but also exacerbates the isolation of existing structures, pushing them farther apart over time. Lack of pressure in sparsely populated areas makes it even harder to build satellites. In places with a lot of matter, gas pressure from the outside can help keep things stable and help proto-satellites hit critical densities. In empty areas, on the other hand, the lack of this kind of pressure means that clouds that could form satellites stay spread out and can't come together into solid, gravitationally bound systems. The absence of post-merger debris fields also plays a significant role. In dense clusters, galactic mergers often leave behind tidal debris which can coalesce into secondary satellite systems. Sparse regions, however, experience far fewer mergers, eliminating this pathway for satellite formation. Without the raw material provided by these interactions, the number of satellites in these regions remains minimal. Faint stellar streams found in sparse regions may offer clues to the missing satellites. These streams could be remnants of early satellite systems that failed to stabilize. Disrupted by weak gravitational forces or cosmic flows, these proto-satellites may have dissolved into diffuse streams of stars, leaving behind only faint traces of their existence. Ionization zones within sparse regions also contribute to the absence of satellites. In these zones, free electrons prevent gas from recombining and cooling, stalling star formation. Without the ability to recombine into neutral gas, the material needed for satellite formation remains in an ionized state, incapable of gravitational collapse. Void halos in sparse regions also lack the dynamical heating found in denser environments. Dynamical heating, caused by interactions between nearby mass concentrations, helps stabilize proto-satellites by preventing gas collapse into overly dense regions. In void regions, the absence of these interactions leaves halos under-energized, unable to reach the conditions needed for stable satellite formation. The lack of shielding structures exposes sparse regions to over-ionization from UV radiation. Without nearby galaxies or clusters to block high-energy photons, these regions are bathed in radiation that strips gas from low-mass halos. This prevents the gas from cooling and condensing, leaving potential satellites as barren, invisible halos. Some proto-satellites in sparse regions may have existed but failed to retain coherence. These structures, unable to achieve sufficient gravitational confinement, dissipated into faint intergalactic gas clouds. Over time, these clouds merged with the surrounding intergalactic medium, erasing any evidence of their initial formation. Void tides, which are caused by gaps growing and stretching, make new satellite material even less dense. Matter can't form tight systems that are held together by gravity because of these weak but constant forces. This creates a setting where proto-satellites are stretched into broad structures that don't form into clear galaxies. Cold mode accretion, a process critical for the formation of smaller galaxies, is nearly absent in sparse regions. In denser environments, gas cools rapidly and flows into forming galaxies, fueling their growth. In sparse regions, gas remains too diffuse and hot to condense, eliminating a primary pathway for satellite development. Some potential satellites in sparse regions exist as hyperdiffuse mini-halos, with densities too low to support significant star formation. These halos, while gravitationally bound, are almost invisible, containing too little luminous matter to be detected. Their presence can only be inferred through weak gravitational interactions, making them some of the most elusive objects in the cosmos. Intergalactic heating contributes to the evaporation of gas reservoirs in these regions. Weak halos, unable to shield their gas, lose it to the ambient intergalactic medium. This evaporation leaves behind faint gravitational shadows, the only remnants of what could have been proto-satellites. Within these shadows, microstructures may exist, detectable only through their weak gravitational influence. These structures, composed of diffuse gas and sparse stars, represent the most basic building blocks of satellite galaxies, frozen in an undeveloped state. Cooling times in sparse regions are anomalously long, further delaying satellite formation. Gas within these regions takes billions of years to lose enough energy to condense, a process that is often incomplete before the gas disperses. This extended timescale prevents the timely formation of satellites, leaving sparse regions devoid of smaller companions. Early supernova bursts in sparse regions may have destroyed fragile proto-satellite systems. Without the shielding effects of nearby mass concentrations, the energy released by these explosions dispersed gas and disrupted the gravitational cohesion of forming satellites. Excessive angular momentum in proto-satellites can also prevent their collapse. In sparse regions where interactions with other galaxies are rare, proto-satellites retain their initial angular momentum. This rotational energy keeps them from condensing into compact systems, leaving them as diffuse, unobservable structures. Galactic marvels, the Milky Way. The Milky Way is a barred spiral galaxy, a grand cosmic disk roughly 100,000 light-years across and about 1,000 light-years thick. Its structure can be divided into several distinct regions, each playing a unique role in the galactic story. At its center lies the galactic bulge, a densely packed region of old stars arranged in an elongated bar-like shape. Surrounding this is the stellar disk, which contains the iconic spiral arms that wind outward, like celestial rivers carrying the galaxy's youngest stars, gas, and dust. Beyond the spiral arms, the galactic halo, a sparsely populated spherical region, extends far into intergalactic space. This halo contains some of the oldest known stars in the galaxy, as well as globular clusters, dense collections of stars that orbit the Milky Way like ancient satellites. Hidden within this halo is an invisible framework of dark matter, an enigmatic substance that accounts for most of the galaxy's mass and exerts a gravitational pull that holds the entire structure together. Without dark matter, the Milky Way's stars and spiral arms would fly apart into the void. At the heart of the galaxy lies one of its most awe-inspiring features, Sagittarius A star, a supermassive black hole with a mass equivalent to 4 million suns. Although invisible to the naked eye, Sagittarius A** exerts a powerful gravitational influence on the surrounding stars, causing them to whirl around it at incredible speeds. Occasionally, this black hole consumes stray gas and dust, releasing bursts of high-energy radiation, a stark reminder of its hidden power. Yet the Milky Way is far from static. Its spiral arms are nurseries for new stars, particularly in regions like the Carina Nebula and the Orion Nebula, where clouds of gas and dust collapse under gravity to ignite nuclear fusion. These star-forming regions inject vitality into the galaxy, ensuring the continued cycle of birth and death that defines its evolution. Within this dynamic environment lies the galactic habitable zone, a region where conditions are just right for life as we know it. Here, stars are spaced far enough apart to minimize catastrophic interactions, but close enough to foster the heavy elements necessary for planetary formation. The history of the Milky Way is written in the stars and the remnants of its past mergers with smaller galaxies. Stellar streams, such as the Sagittarius stream, are the remnants of dwarf galaxies that were torn apart and absorbed by the Milky Way's gravity. These streams trace ghostly arcs across the sky, whispering tales of galactic cannibalism and the relentless pull of gravity that shapes the cosmos. The future of the Milky Way is equally dramatic. In about 4.5 billion years, it will collide with its nearest spiral neighbor, the Andromeda Galaxy, in a cosmic dance that will reshape both galaxies. Despite the seeming violence of this event, the vast emptiness between stars means few actual collisions will occur. Instead, the gravitational interplay will warp and stretch the galaxies, eventually merging them into a new structure, likely an elliptical galaxy nicknamed Milkomeda. In the middle of all this magnificence, there remains a harsh reality. The Milky Way is distinguished by its void as much as by its stars, despite its splendor. The immense distances between celestial bodies serve as a stark reminder of the vastness of the cosmos and the precariousness of the bonds that bind it. But it is in these empty areas that the galaxy's actual splendor, a complex ballet of energy, matter, and gravity against the still background of infinite space, emerges. Cold hydrogen pockets in deep voids. Cold hydrogen pockets in vast spaces are among the universe's most mysterious occurrences. The absence of external factors permits these primordial gas reservoirs to survive in unusual and interesting ways at the cosmos's emptiest areas. Hydrogen interacts differently in these spaces, revealing the early cosmos and its dynamics. One distinguishing aspect of these pockets is the suppression of 21 centimeters hyperfine transitions. In typical surroundings, hydrogen atoms emit modest 21 centimeters radiation, owing to quantum mechanical spin shifts, which is an important marker for astronomers charting intergalactic hydrogen. However, in deep voids, the near-complete lack of particle collisions limits the frequency of these transitions. This suppression renders these pockets practically undetectable to traditional radio observations, allowing them to stay undiscovered by most surveys. Within these pockets, hydrogen atoms may remain in specific quantum states for billions of years. Without external perturbations from radiation, collisions, or nearby gravitational influences, the atoms are able to freeze in low-energy configurations. This quantum stability preserves a snapshot of conditions from the early universe, effectively locking information about their primordial state into the present day. These hydrogen pockets are thought to be relics of pre-galactic epochs, remnants of a time before the first stars ignited. In denser regions, hydrogen clouds underwent gravitational collapse, forming galaxies and enriching the gas with heavier elements. In voids, however, this process stalled, leaving behind untouched reservoirs of pristine gas. These pockets may contain isotopic anomalies, such as higher ratios of deuterium, reflecting primordial nucleosynthesis conditions and providing a glimpse into the universe's chemical infancy. It is also known that cold hydrogen spaces in voids are very good at keeping heat from moving around. When these areas are away from heat sources like stars or galactic activity, they can cool to just above the cosmic microwave background temperature, about 2.7 K. Quantum cooling effects take over in these situations, keeping hydrogen atoms in very low energy states. This almost perfect separation keeps kinetic energy from building up, which makes the clouds even more stable. Due to slight density gradients within the clouds, hydrogen pockets can cast faint absorption shadows on distant light sources, subtly altering their spectra. These shadows reveal the shape and distribution of the gas, providing an indirect way to study these elusive structures. There are times when gravity waves can pass through these areas and cause small problems. It's possible that the few hydrogen clouds could work as natural echo chambers, making the effects of these waves stronger or changing the way they travel. These kinds of events might provide a unique way to study both gravitational waves and the movement inside gaps. Electrostatic stabilization may also play a role in preserving the structure of these pockets. Weak electrostatic forces between hydrogen atoms counteract the minimal gravitational pull in voids, preventing the gas from dispersing completely. This balance allows the pockets to maintain their integrity over cosmic timescales, despite their low densities. Non-linear wave dynamics occur when hydrogen pockets interact with faint intergalactic sound waves. These interactions generate unique waveforms that ripple through the gas, creating patterns that are difficult to observe but hold valuable information about the local void environment. These waves are not just markers of activity, but also agents of slow, subtle change within the pockets. Molecular clustering is another rare phenomenon within these pockets. Trace amounts of molecular hydrogen can form under specific conditions, facilitated by interactions with microscopic intergalactic dust grains. These molecular clusters may exhibit behaviors entirely unique to void environments, where they are free from external disruption. Cosmic tidal forces also play a role in the evolution of hydrogen pockets. Weak but persistent, these forces stretch and dilute the gas over millions of years, creating elongated structures. This gradual evaporation of hydrogen contributes to the overall expansion of voids and the redistribution of matter across the cosmos. Temperature plateaus within hydrogen pockets reflect their long-term stability. Unlike dynamic environments where temperatures fluctuate due to heating or cooling events, these pockets exhibit near-uniform thermal conditions. This constancy is a result of minimal energy exchange, highlighting the equilibrium state that defines void environments. Within these pockets, hidden substructures may exist as faint density variations, too small to trigger star formation. These internal fluctuations, while subtle, could influence the distribution of matter within the pocket and act as seeds for future evolution if disturbed by external forces. Long-wavelength electromagnetic resonance is another intriguing possibility. Hydrogen pockets in voids may resonate with ultra-long wavelength waves, creating faint but detectable signals. These resonances could provide clues about the physical properties of the gas and the larger void structure. Rare chemical reactions occur when hydrogen interacts with trace amounts of intergalactic dust. These reactions, driven by the extreme isolation and low temperatures of void environments, could result in the formation of unique molecular species not observed elsewhere in the universe. Studying these reactions offers a glimpse into chemistry under near-perfect vacuum conditions. Some hydrogen pockets hover near the critical density for gravitational collapse, but remain in a suspended state due to the absence of external triggers. These on-the-verge clouds are potential sites for delayed star formation, waiting for a disturbance to tip them into activity. Such an event could occur billions of years after the pocket's formation, making it a time capsule of cosmic potential. At void boundaries, hydrogen pockets may experience compression from converging gas flows. These temporary density spikes do not lead to sustained star formation, but create localized regions of higher density that can alter the pocket's overall structure. Observing the distribution and dispersal of hydrogen pockets allows you to measure the expansion dynamics of voids. As voids expand and their contents become more diffuse, the growth of these pockets acts as a natural indicator of cosmic expansion. In rare situations, intergalactic collisions or merging gas flows may destabilize these pockets, causing a chain reaction of events that leads to star formation. While exceedingly rare, such events would result in a profound alteration of these previously dormant reservoirs. The emptiest parts of the universe hold some of the biggest mysteries, revealing how the cosmos evolves and what it's ultimately heading toward. There's so much more to uncover in these desolate regions, and the journey has only just begun. What other wild concepts would you like to hear about? Comment down below, and if you enjoyed this video, consider leaving a like and subscribing to the channel. Thanks for watching.